Multi-agent systems have been proposed as a solution to a variety of problems ranging from precision agriculture to remotely accessible robotics testbeds. Often, for simplicity, these algorithms abstract the underlying dynamical systems as single integrators. In the case of differential-drive mobile robots, one such method considers a single integrator point placed at a distance L in front of the robot. If the planar single integrator point has a control input of linear velocities u sub si, then taking a derivative yields a diffeomorphism f between the dynamics u sub si and the linear and angular velocity of the mobile robot. That is, f converts between the control input to the single integrator and the control input to the mobile robot. It turns out that the diffeomorphism is actually a function of the distance L. The question becomes, how closely should the point be placed to the robot? Well, if the point is too close, then the robot has to perform complex maneuvers to keep up with the point's maneuvers. If the point is too far away, then the robot does not closely track the trajectory of the single integrator. We want to place it at just the right distance. Let's look at an example. This is a group of mobile robots in the robotarium performing consensus. This first video places the point at a large distance in front of the robot. The robot's motions are smooth, however, they end up fairly far away from each other. In the second experiment, the point is placed very close to the robots. The robots meet much closer than the first time, but they move erratically. In this last clip, the point is placed at the average of the last two distances, and the robots meet and move smoothly. These examples show that picking this distance may require some tuning. To avoid this procedure, this paper offers an optimal control-based method for automatically selecting this parameter over a variable time horizon. In general, this work considers the following optimal control problem, where the decision variables are a parameter, p, and the time horizon, delta t. Because these values are just real numbers, this paper shows that the previously listed problem can be solved with a gradient descent-based method. This algorithm solves general parameter selection problems. However, this work applies the previous algorithm to the single integrator abstraction that we discussed earlier. To do so, this work formulates an appropriate cost metric that trades off precision versus maneuverability. This video shows the algorithm in action. In particular, a single integrator is tracking an ellipsoidal reference using a simple proportional controller. This controller is mapped onto a mobile robot using the aforementioned abstraction. On the long portion of the ellipse, the parameter is shortened and the time horizon is lengthened, providing better reference tracking and prediction. On the short sides of the ellipse, the parameter is lengthened and the time horizon is shortened to account for the increased maneuverability requirements.